All right, everyone, welcome to today's seminar. It's my great honor, and I'm very proud. This is my first graduate student that come through my program. So Isabelle Van Benschoten, she's going to talk about her work on the correspondence between soil organic matter transformations and carbon emissions in wetland soils. But to give a little bit of background about Isabelle, she's from Wappingers Falls in New York State. She actually did some environmental science projects early on that involved capturing eels in the Hudson River. She was an undergrad in our department, and during her undergrad, she actually worked in a micro lab, sampling water samples from around campus during the pandemic and monitoring COVID. She actually got on a publication from that work as an undergrad student. She was recognized as an outstanding undergraduate by the college. When she started her graduate work with me, she received the Dean's Scholarship. She's received travel scholarships to attend big conferences in our field, like the International Goldschmidt Conference and the American Geophysical Union Conference. One of those, the Goldschmidt Conference in 2023, we were in Lyon, France, and that was one of the highlights of my career, if I'm being honest. For Isabelle too. She's taught courses. She loves to teach. She's very passionate about teaching, and both faculty and students alike recognize her as a very effective, powerful teacher. She's taught the IDEA course several times, which is like this think tank innovative undergraduate course. And she's also been filling in as the instructor for ENST 200 this semester on top of finishing her graduate work. So I think that's amazing. And from what I hear, she's been doing a really good job. And so I just want to thank Isabelle on behalf of myself and the department for, she's been really important for keeping undergraduates focused like on our program and bringing new students into our program. And I also wanted to point out the fact that she literally had to build our lab from scratch before she started her research. So that's an amazing thing, to be planning your research, and then step one is build the lab. And she did that, and I'll be forever grateful for that. So the other thing I want to say is that for graduate students and advisors, we all know that things come up during our graduate work, right? Challenges, global pandemics, machines blowing up, computers crashing, work day, not really working any day. And Isabelle's been working just diligently through all of that, and always positive, always around it. And she's got a job lined up at the Smithsonian Environmental Research Center. And she'll talk about that today the best way she's done her work. So I'll shut up now, and Isabelle will take it.
Well, thank you so much, Jared. Thanks, guys. In essence of me also not getting sappy and having a lot to tell you, I'm just gonna jump right into it. So just to give you an overview of what we're gonna go through, I'll start with some background and the goals of the project, then get into how we did it, talking about the gas emissions that we found from these incubations and how they really corresponded to this soil organic chemical profiles. Then get into some seasonal variation in emissions and conclude future directions and hopefully have some time for questions. So we all know that wetlands have an incredible amount of ecosystem services, one of which being carbon storage. They store about 20% of Earth's carbon while only taking up about 5% of our land surface. We also know that they're one of the largest emitters of methane. They're the largest natural emitters, accounting for about 1/3 of emissions. And really, the organic chemistry of that soil is what's driving these emissions. In addition to these inundation factors, how is this redox condition really playing a role? What is the plant cover doing? And how are the microbiology, how is that community kind of also influencing this? And these microbes can do this through, there's some nuance to this, but through three main pathways: hydrogenotrophic methanogenesis using carbon dioxide and hydrogen, acetoclastic using acetate giving us carbon dioxide and methane, and methylotrophic using methanol and other single carbon compounds giving us methane and carbon dioxide as well. And it used to be thought that these microbes were only able to survive in these highly reducing anoxic sediments. They were obligate anaerobes. But we now know that some of them can survive in upwards of 20% oxygen in these short periods of time through a couple of different ways, which is partially why we're able to understand that some studies have shown 90% of methane generation coming from these periodically oxic systems. And these, like wetlands, are the most dynamic systems that we have, dealing with different redox changes, including these 6 hours tidal changes, as the tides are coming in and out, dealing with saturation and salinity, in addition to these diurnal 12-hour day-night cycles driven by plants. And these are really driven through this wetland plant adaptation called parenchyma, this hollow porous structure that's really efficient at transporting gases not only from the atmosphere to the rhizosphere, that soil that's coming in contact with those plant roots, but also from the rhizosphere to the atmosphere. This tissue, like I mentioned, really porous. I think it kind of looks like osteoporosis bones in those x-rays, but really efficient at transporting these gases. And one of the most effective and aggressive oxygenators is Phragmites australis, this invasive species that is globally distributed and really able to take over these systems through their dense network of roots and rhizomes. And they have a unique life cycle in which their old stands, their old shoots, stay up during their senescence and can kind of fall over, leaving these pipes that really allow this effective gas transport out. And as they go through, their shoots kind of come up and start to continue to go. And this starts again in the next season. And you might ask, how do we see these fine scale redox changes? How do we know that oxygen is actually getting to the rhizosphere? Now, Lenczewski and their team used these aptode foils, which is where this fluorescent sheath comes in contact with the sediment and can give us these really cool 2D kind of spatial maps of where this oxygen is. Not only can we see this in the spatial dynamic, but we can also see it temporally, given that we can get these snapshots over time and see how this plant is really transporting these gases. With this is important with Phragmites because this is different depending on where these roots are and what kind of root they are. During these main roots, we're getting really effective gas transport, kind of pretty variable in these lateral roots, and rhizomes themselves don't really leak that much oxygen. These main roots, in addition, it was really effective from the root tip, where it was growing from, which adds another kind of spatio and temporal dynamic as these roots are growing into the system. How is that influencing the soil carbon there? So with this, we know this is an incredibly dynamic system. We have our water table moving. We have these plants operating on these 12-hour cycles, all culminating together over these different spatial scales, whether this is in a single wetland or over the Chesapeake Bay watershed. And this is important when we're thinking about the redox ladder or how these redox dynamics are impacting things. As we move down this ladder, we're getting into more reducing systems and less energetically favorable reactions occurring. And this is important because we know that oxygen is one of the soil master variables, really influencing these things both biotically and abiotically. And we think often about these redox couples and how they work, but when we think about the microbes, they need three things. They need an electron acceptor, an electron donor, and a carbon source for anabolism. And this electron donor in these incredibly organic systems is going to be this carbon. Now, we think a lot about these couples driving the energetics of these systems, but this carbon source is also important and not always really given the credit that it's due. When you write these equations down, you're often writing just the simplest form of carbohydrates rather than acknowledging how complex these structures can be. And thinking about these two-sided stories is important when we think about what microbes are really able to go through these processes. Are some of them able to break down these larger structures? Can some of them only get into certain parts? Some microbes are able to reduce manganese and iron. Some can only reduce one. Certain microbes can only do some of these processes in certain conditions. So it's important to kind of give the nuance and the credit that these kind of structures and systems can do. So really acknowledging the two sides of the story. Not only are we dealing with this redox ladder, but also this organic chemistry component as well. And I know thermodynamics is a scary word, but it's not, because energetics really do drive these systems. How is this kind of soil organic continuum being influenced by oxygen's presence? How are these microbes being influenced? Are we getting this kind of trophic degradation into the substrates for carbon dioxide and methane generation? And we don't have to get into the nitty-gritty of this diagram, but what's really cool is that each of these carbon molecules has its own unique energy contribution. They're donating a certain amount of energy. That's what this nominal oxidation state of carbon is. How likely is it to donate its electrons or keep them? So with each of these having their unique pool, it's the higher your nominal oxidation state, the more electrons you can provide, and typically the more bioavailable you are. We get this really nice linear relationship. So we really want to see, how is this oxygen transforming these organic carbon reactions, and how is this facilitating potentially this trophic cascade toward carbon dioxide and methane emissions? We really think that these short redox perturbations can increase carbon emissions, partially because these smaller, more oxidized organics are going to be easier to be utilized by those microbes. So we really want to see kind of how is this organic chemical profile corresponding to these emissions over different time scales, whether this is over a season or an entire wetland, on these space and time scales. So with that, I will get into how we did it and where we looked. Like Jared mentioned, we got the chance to work at the Smithsonian Environmental Research Center over in their Global Change Research Wetlands in Edgewater, Maryland. This was a super cool site, phone service, boardwalks, bathrooms, very lucky. And I'm super excited to continue to explore a different part of the marsh. But we worked over on, this is off of the Road River, which is an oligohaline marsh of a salinity of about 6 parts per 1,000. So for those of you who are not in the marsh as much as us, it's like moderately salty. pH is about 6. We have this transect that's a little bit less than 200 meters, and our bulk pore water collection site in the blue. Just to give you an idea of what this looks like in the growing season, these stands of frag are incredibly dense. I mean, we were boxing this Phragmites out, trying to get any sort of space. This is the pore water collection site, and Jared's standing on this dock that's over that tidal creek that was right adjacent to Site 1. Site 1's like probably right about here. And this is that tidal creek you can see in the site map. In the after the growing season, you can see it's a lot more browned up. You can also see, not quite tall enough, but the heads of the frag are senesced, they're a little bit fluffy. So going through these different cycles with still a really dense system that we're dealing with. So with that, I can talk about the cores. Can't have a soils presentation without some pictures of cores. So our Site 1, our creek adjacent site, really had this really incredibly large organic mucky layer, and you can see the roots and rhizomes throughout it. Our Site 2, a little bit shallower organic here, still really mucky, still really sticky. Once we hit about 35 centimeters, we were dealing with this really fibrous peaty layer. You can also see this really thick rhizome there. These are some of the thickest rhizomes I have ever seen. It's pretty incredible. Technically still soil. When you touch it though, it's really just plant material and water. 2 important parts of soils, I must say. With our Site 3, still this really organic layer at the top, sticky, still organic throughout, but we can tell from these bandings of these orange and greens and blues that I think it's a pretty core. But you can tell this is getting more mineral, getting a more clay layer, still getting these redox features. You can kind of see this over time as we move out of the wetland. Our really mucky organic layer is kind of getting smaller. So with that, we took 6 cores perpendicular to our transect, and we collected soils from where the roots and rhizomes were most dense. Depending on the core, it was either between 20 and 40 centimeters. We collected our pore water from here, taking a core and kind of collecting the water as it recharged through. And with that, we took them back to the lab, homogenized it, picked out the roots and rhizomes by hand, and got them in bottles within the day. It was a really long day. Thank you to everyone who helped in advance, which was really cool. We got them back to the lab and immediately flushed them with nitrogen to initiate anaerobic conditions. This is what they looked like in real life. They're about like yay big. And we went through a destructive sampling scheme, meaning that each week we took a set of these bottles and put them into the freezer, stopping the incubation. At the conclusion of the 3rd week, we gave them 3 pulses of oxygen, giving them a final headspace of about 3.5%. And we sampled their gases on a GCFID about every 3 days to get an idea of how these emissions were changing. And we can see here, we have our days incubated on the x-axis, our carbon dioxide concentrations on the y, and our sites 1, 2, and 3 corresponding with the map up in the top left. Now, all of these points were from before the oxygenation pulse, and we collected all of these samples before the growing season. So those soils there weren't experiencing these intermittent pulses as frequent get in the season. Site 3, our forested edge site, really came to play, coming up pretty strong, much higher than sites 1 and 2. And after our oxygen pulses, we can see here that Site 1 really came up, had the most dramatic increase in methane compared to the other 2 sites. Now looking at our methane emissions, now here sites 2 and 3 coming much higher than site 1 before oxygenation pulses, shown by these 3 vertical lines. And site 1, a small blip in methane here, but after those oxygen pulses, a dramatic increase relative to the other 2 sites. Now, given that we're still getting a pretty constant, a slight increase in the average methane concentration of those 2 sites after oxygenation, we'd imagine that some of that methane would be oxidized into CO2. So given we're having this kind of constant emission, I'd imagine those emissions kind of still occurring. So with that, soils from site 1 really displayed this burst of both CO2 and methane immediately following those oxygen pulses, which is important because they're the most inundated site, the most central of the marsh, still having periodically like intermittently throughout their time, but not as much as our other 2 sites. So with that, I'm also going to acknowledge the incredible variability. I'm not going to pretend I didn't see those huge error bars on those graphs, which is important. We always say that emissions are variable. We always say that soil is heterogeneous, but with that, we really need to kind of understand how is the carbon chemistry, that molecular profile, changing, and is it corresponding to these emissions? And how is this being influenced by this kind of trophic cascade of carbon? So with that, I'm going to get into those molecular profiles and how they correspond. So like I mentioned, we stopped those incubations, giving us a snapshot of that carbon chemistry each week during the total period over that 1-month incubation. So we took those solids, extracted them from the bottles, and aliquoted them into 2 ml tubes, spun them down to separate the solids and the liquids, and we ran those liquids on FTICR-MS. Now, FTICR-MS, or Fourier transformed ion cyclotron resonance mass spectrometry, a word that just keeps on giving, which is really cool. I mean, FTICR is arguably the queen of mass spec. We're dealing with a 15 Tesla magnet, giving us an ultra high resolution capacity. I mean, Dr. Farquhar in geology has a machine about the quarter the size of this room, and it's still not able to get the resolution that this machine is. His machine can also do gases, so it is really cool. Every analytical technique has its pros and cons, but I do think this is an incredible machine. And it works. How much you ask? I will tell you. So what it does is we inject that liquid into an ionizer. It gently ionizes these, giving them a charge, which allows them to be influenced by that magnet. And as it orbits around this magnet, they're going to begin to separate based off of weight. Heavier things are going to go slower, lighter things are going to move faster. And these detectors aren't magic. They're not able to say, molecule 1 is on lap 32 and molecule 3 is on lap 4. They're just picking up a signal. So what they're picking up is this really complex wave that's forming. And with that complex wave, what they can do is a Fourier transformation on it to give us our spectra. So for a complex wave, giving us our spectra. And this Fourier transformation, if I can click out of this, is pretty cool. It takes this complex wave and breaks it down into individual constituent waves, each of these being a unique molecule in the sample. Now, we know it's a unique molecule based off of its mass. This frequency of orbit is based off of the mass, so we know that that is going to be a function of it. And the amplitude is going to be a function of its intensity, which we can think about as how much of that molecule was detected in the sample. So with that, we get such an accurate mass that we're actually able to predict the chemical formula of these molecules, giving us an idea of how many carbons, oxygen, nitrogens, hydrogens that are there. With that, we could do a couple of other cool things. If I could get out of the video. We can calculate the nominal oxidation state of carbon, like I mentioned, that NOSC, giving us an idea of the bioavailability. Calculate the double bond equivalence, kind of getting an idea of how many double bonds are in those side chains. We can also calculate the aromaticity index, or how aromatic, these benzene rings with our double bonds throughout them, giving us an idea of what these molecules are kind of looking like on a broad scale. We can also construct these Van Crevlin diagrams. Now, they're really cool in that each molecule detected is going to be plotted. Each one of these dots is a unique molecule, creating this pretty cool fractal pattern when we plot its oxygen to carbon ratio against its hydrogen to carbon ratio. Now, what's even cooler than the fact that they look pretty and like snowflakes is that each of the regions in this graph corresponds to a molecule type. And this is really important when we think about kind of what is the spread of the molecular composition within these samples. And we can do that with a sample like ours, but we noticed this region was changing quite often in our samples, and there wasn't quite a region defined for it yet. And that region, once we went into the literature, was often called CRAM, this carboxylic rich alicyclic molecules. So we have our carboxylic groups here. We also have these alicyclic rings, meaning that they don't have those double bonds throughout it. And you might think, well, double bonds would be harder to break. They're going to be more work for these microbes to get to. But sometimes with these single bonds here, we're dealing with some stereochemistry. If you remember back to building those molecules, when you have those double bonds in there, you're not really able to get as much twisting. But with these single bonds, you can have these carboxylic groups, as reactive as they are, spin around, blocking those microbes from actually able to access that carbon. Still bioavailable, still able to access it, but maybe not as easily as we might think. The other region that we found to be really interesting and kind of variable was our lignin-like molecules. And we know lignin molecules are these large, complex carbohydrate kind of chains that are from plant material. They're really big, really hard to degrade. Literature is they're still out thinking about that though. And you could imagine that with each of these diagrams being one of our samples, all of the molecules in this, and this only being a subset of our samples, this was an incredible amount of information to get back. And with that, all of this information is kind of this multi-dimensional data cloud is how we think of it. And what's an easier way to do it is we can take this multi-dimension and plot it on 2 dimensions that we can understand, giving us an idea of the variability within our data set, called the principal components analysis. Now, this principal components analysis captured about 45% of the variability in our data, 30% on PC1, principal component 1, that x-axis, 15% on PC2. And what's really cool about this to me is that regardless of how long these soils were incubated, we were able to see that they grouped by their site, kind of really shedding some light on the organic carbon chemistry that was really innate to that site in particular. And each of these ellipses going around each of the different sites and our pore water up at the top. And this is the same PCA, so don't get overwhelmed, because I did when I first looked at these. But what we can also do is see which molecules really correspond to which principal component. So here we can plot the molecules that correspond with positively on PC1 in blue, negatively on PC1 in orange, similarly with PC2 positive and negative. And we can plot these like the molecular weight compared to their hydrogen to carbon ratio, or we can plot their molecular characterization with those Van Crevelen plots like I talked about earlier. Since there's a lot of information to kind of digest with these, I thought it might be easier to walk us through site by site, giving us an idea of what these molecular profiles looks like over per site and kind of over time. So, imagine we all just got to the field, we're walking through the forest, we got to site 3, we're ready to start the day in the field. And we're like, what are these molecular profiles looking like? Well, we saw these grouped pretty correlated along PC1 positively. F0 is going to be our incubations that were incubated for 24 hours to kind of hit an equilibrium. F1 was our 1 week, F2 2 weeks, F3 3 weeks. That was when we did our oxygen pulses after that. We have our F4 here. Really a lot more correlated along PC2 in the negative direction. So looking at these molecular weight diagrams, before oxidation, we were having these much heavier molecules here, compared to after PC2, a much lighter shift. We're moving from heavier molecules to lighter molecules after that oxidation. Now looking at the Van Crevelens, we can see we're dealing with this lignin pool here, pretty densely in this PC1 positively. But what I do want to point out is they're shifted more to the right here. We would think about these as being more oxidized lignin pools, given that it has a higher oxygen to carbon ratio. When we think after the oxidation, that F4 that was correlated along PC2 in green, we can see we're still dealing with this lignin pool, but it's much more diffuse. There's a lot less of them. We're seeing an enrichment in that CRAM region, like I mentioned earlier. Oh, nice arrow. And when we think about our methane concentrations here, we saw that the forested edge site, that site 3 in green, really did produce methane throughout the anaerobic portion of the incubation, remaining pretty constant afterward. Now, moving along to site 2. We can see site 2 here, mostly correlated negatively along PC1 in that orange. So negatively with PC1, our transitional site, we're seeing a lot lighter molecules like I mentioned earlier, and we're also seeing an enrichment in these cram-like molecules here. And this transition site was our highest methane producer throughout the entire incubation, which is really interesting to us. We're seeing kind of these relationships grow between these lignin pools and these cram pools. Moving along to site 1. Site 1 was unique because it didn't really have much methane production. This one being predominantly correlated along PC2 positively, except for this P0A, which is much more correlated along PC1 negatively. So looking at that, it has a much lighter molecular pool in that P0. Then moving to the other, the P sites, those site 1s, we're dealing with a lot heavier molecules here. When we look at the Van Crevelins, not only are they they're enriched in these large molecules, but they're also reduced in these large reduced lignin pools, which is also interesting because site 2 was anti-correlated with site 3. We think about it, we're talking about the orange compared to the blue. Now this anti-correlation was interesting to me given that these two sites were pretty close to each other on the transect, but we're really seeing this change in the reduction of these lignin-like molecules and how much shifted they were to toward heavier ones. And when we look at this over time, it makes sense that we're dealing with this site. So sorry, let me orient us to this graph because this one's a lot. This is just like these other Van Crevelin diagrams like we were looking at. We have our hydrogen to carbon ratios on our y-axis. Our oxygen to carbon ratios are on our z-axis this time, and we're looking at a time series over time here on the x. Our time 0 was going to be our 24-hour incubated, 2, 1, 2, 3, and 4, 2, 3, 4 weeks. And we also had our oxygen pulses here. And we can see there's not really a lot of molecules present in our T0 site for P1, which is partially why they were probably so much lighter if we think back to that principal component and that weight. And it's also, we can see it took a lot longer for these heavier carbon, these more carbon-rich molecules to come into solution in this T1, which to me could be a couple of different things. Site 1 was right near that, tidal creek. And that tidal creek really could have been washing out the more labile, lighter carbons easier, but it also could have been depositing these heavier carbons. So which side of the story that is, if that's even true, we don't know, just an idea. But I do think that these heavier molecules must have taken longer to come into solution, which is why that 24-hour equilibration period wasn't quite long enough, why we took a little bit longer. But we can see here, if we circle what I think would be this cram pool, we can see kind of a production in it in our site 1 here, kind of a disappearance here and here, and then a resurgence again in our site 4. And if we look at where we got this, our methane, we got this small blip of methane that I was originally convinced was just a machine error. But now looking at this molecular data, there is something to this, potentially. And we can see here we got this methane again in week 4 after that. So we're kind of seeing this relationship between CRAM, this carboxylic-rich alicyclic molecules, and the methane. Now, there's obviously a ton of different ways this could have happened microbially with degradation. The lignin could have been, methylated into a methoxyaromatic, could have turned into CRAM, anything that could have been the substrates for fermentation, really giving us acetate and carbon dioxide, what we need for acetoclastic methanogenesis, also yielding what we would need for hydrogenotrophic. And it wouldn't be shocking to me if we got a single carbon compound and that was fueling methyllotrophic methanogenesis. So I do really think there is some relationship between this CRAM pool and the lignin pool, and whether that lignin is more oxidized or more reduced, and how much methane we're getting from those different pools. And whether this CRAM pool is a precursor or an effect of this methane degradation or this methane production, that is still up for debate. But we do really think that these redox perturbations are increasing the carbon emissions, and this is potentially due to these smaller, more oxidized soil organic material being present, fueling this generation. So with that, I'll get into our seasonal variation in our growing season and not growing season. information. Like I mentioned, this is an incredibly dynamic site. We were dealing with soils that hadn't been oxygenated by that frag in an entire season. Now moving into the growing season in July, we were able to see what is happening with these emissions after these plants had kind of exhibited this oxygenation to the soil. So we went and did the pretty much exact same thing, both in March and July, this time in the frag growing season when we were experiencing this, going with the same destructive harvesting scheme and sampling gases, this time running them a little bit longer, having more groups. We had a lot less bottles break, and we were like, it'd be really cool to see this go longer. So that's why the lines are longer. They go a little bit further in our July, that growing season solid line, and our pre-growing season, the dotted line, still split out by site, and our oxygen pulses coming in the third week by those black vertical lines. And we can see here that we're dealing with this kind of lack of response in carbon dioxide emissions after that oxygen pulse, which was not the case in our pre-growing season. So across the board, these oxygen pulses really stimulated these higher carbon dioxide emissions in the pre-growing season soil relative to that of the growing season. And I also wanted to point out in site 3, that forested edge site, we saw virtually no change in carbon dioxide emissions, which is pretty insane given the fact that we saw at least some variability amongst the other sites. And this is partially potentially due to the fact that we were dealing with maybe less organic material in those soil profiles. So it could also be because the plants, this was when, as these plants kind of colonized across the marsh, this was the last area to be colonized. These also could have been exhibiting more oxic conditions throughout the entire season, given their more upland position. In terms of methane, like I mentioned, we saw the biggest increase after oxygenation in our site 1 in our pre-growing season. Much variability amongst our growing season soil, but still significantly lower on average than that of our pre-growing season. So taken together, I do really think that these plant-mediated oxygenation events could prime or stimulate methane and CO2 production in the field, whether this is over short-term, short spatio or temporal scales, or long. Are we looking at these plants over the course of a day, over the course of a month, a season, or years, as our climate continues to change and sea levels begin to rise? We could be seeing this Phragmites take over different parts of the marsh. We're going to be experiencing yet another redox dynamic in these systems. So I do really want to point out, if you got anything away, take anything away from this talk, that this carboxylic-rich alicyclic molecular pool is really a unique signal of methane production. Like I said earlier, whether this is a precursor or an artifact or something other of the sort, this cram pool really does seem to signal something with this methane emissions. And I think it would be really cool to take some lignin and have it be isotope traceable. And we can kind of see how it shifts from the solid to the liquid to the gas phases, and see kind of how it's being degraded both anaerobically and aerobically. Getting a microbial characterization of these solid profiles, like I mentioned, we took the liquid for FTICR. That solid we still have. It'd be really cool to get some microbial information on it. And as a little bit of an aside, we did see in the literature the use of these metal inoculants to kind of initiate anaerobic lignin degradation. And there was a lot of different kind of things we saw with that, but it would be really cool if Dr. Lansing, I don't know if she's here, let us throw one of these bottles in her reactors and see what happened. Could be something with the microbes and their kind of metal catalyst that they have. But the other interesting thing we saw in the literature was the fact that this cram pool was really present in forest fire soils. We're like, that's interesting. Like, what does a wetland and a forest fire soil have in common? And we got to thinking about it, and it really could be an oxygen soil, an oxygen store. Is this oxygen being competed for by the microbes in the plant material, or is it being competed for by that fire? Oxygen feeds a lot of different things. That was just something interesting we found in the literature. But with that, I really want to thank so many people in here. I've been in ENST now for 7 years, crazy enough. But yeah, thank you so much, Dr. Wilman, Dr. Garwood, Dr. Fischel, Dr. Baldwin, and so many of you guys here. And this work really would not have been possible without our undergraduate help. Caroline, Grace, Hannah, Colin, each one of those gas points that you saw was ours across the GC and on the phone with tech support and all of that. You really don't know a machine until it breaks. And yeah, with that, thank you guys. Any questions?
I have a comment, really, then we'll go to Jason. Comment is that that was perhaps the best, most concise presentation of how to do SCR works. I'm not saying that because you're my student, I'm saying because I've tried and failed.
Yeah, did everyone grab that, catch it a little bit?
So would you expect Site 3 or Forest Edge Site to transition and become more like Site 2 over time, or is it because it's further away from the water edge?
I think it's further away.
Or is it fragmented?
I think it's a little bit both. What's interesting about Site 2 is there is that really peat layer there, which people have thought was from a prior Spartina colonization. And I think that forested edge site wouldn't necessarily hit that because it didn't kind of have that succession. I also think it would take an incredible amount of time for that much organic material to build up in such an upland. I mean, I guess it wouldn't be upland anymore, but that's the kind of thing takes a lot of time. So I don't really know if it would transition to something more like Site 2 or if it would be a water and frag story. I think it would be a combination because, I mean, you'll see Phragmites on the side of I-95, you see it in the middle of the marsh. It can go into incredible places. Yeah.
If you were to potentially get a microbial characterization of the solid portion of your incubations, what differences would you expect to see between the 3 different sites, and how do you think that plays into a lot of this chemical characterization work that you've done?
That's a great question. Microbial data is like so interesting. I have preliminary data. I did my senior capstone on a similar transition portion of that marsh, and we got very variable kind of microbes. I do think each site would have its own unique population similarly to its molecular kind of composition. I would expect, I don't know, this is tough because it is tough with this information. You don't get what they're doing, you only get the populations that are there. So I think there's a lot of potential for different things. Sorry, that doesn't really answer your question.
I have a question on
Oh.
I think you can ask her to unmute.
Oh, would you mind unmuting, Dr. Lansing? Sorry.
Can you hear me okay?
Mm-hmm.
Okay, wonderful. So, wonderful presentation. Yes, I think that you're onto something. So we did a lot of work with both digestion and fermentation with micro aeration. And what we suspect, which I think is similar to what you're finding, is that it changes the enzymatic activity when you give these microdoses. And so the metals, for example, and some of the microbes that you're seeing activated, maybe because when you give these microdoses, they're able to kind of activate different enzymatic activity, which enhances some of the methanogenous production. And so we're still kind of investigating that, but I think this is really interesting to look at it from the wetland point of view, and then what we also found with microdosing and our digesters and our fermenters. And but we also saw with the microdosing some increases in methane production. So I think it's super interesting. And we also found increases in just forming the acetate, right? And so with the fermenters, we're just trying to get acetate, which is then used later by methanogens. And sometimes that microdosing helps in creating that acetate quicker.
Yeah. No,
So I think it's really good.
Very cool to hear. Thank you so much.
Did you now the fire thing, I want you to expand upon that a little bit more. So is the idea that the fire, when a forest fire comes through, it needs oxygen to really burn a lot. And so can you explain a little bit how you think that? So the idea is the more oxygen it has, the more like hard the fire is going to burn. And then how does that affect what you're seeing, what's left behind after the burning process?
To be incredibly honest, I this is a little bit of a half-baked idea. It was what we saw in the literature. What could possibly be in common with these forest fire systems? I do not know much about forest fire ecology or effects on soil. I was just really trying to kind of get an idea of what might be the commonality between these two systems.
So one of the things I'll just say really quick, because it is interesting. So one of the ideas I've had for a while, just never been able to pursue it, is that we have a lot of iron in the soils that we're working with in the wetland. So there's a lot of organics, there's a lot of iron. In soils where there's forest fires, there's also iron, there's organics. And there's certain types of organic reactions that happen during a forest fire in the soil. And one of the ideas that I have for the mechanism for how it happens is that there's a catalytic reaction that can happen with iron and organic matter with heat. And there might be some story here too with the redox oscillations that we're doing. So yeah, it's not a great answer, but there's something there.
Yeah, so if there's more iron in forest floors, then does the iron combined with any sulfur that might be there to like reduce sulfate, like when you're reduction with the sulfate reactions happening, so then it favors methanogenesis because the sulfate's not available possibly?
Yeah, so in our system, we definitely have hydrogen sulfide that builds up.
Definitely.
You can smell it. And so the idea though for us, I think, is that these different processes are happening more or less simultaneously because there's so much organic carbon there that the substrates are plentiful to drive all these reactions at the same time.
Okay, interesting.
Please, you go ahead.
Oh, are you sure?
No, we were gonna hear from students.
Oh, okay. I just want to make sure, like, I got your main takeaway about, like, CRAM seems to have this connection with the methane, but I just wanted to make sure, I don't remember I forgot to look at what PowerPoint slide number it was, but I think it was looking at your seasonal data, and I don't remember if it was, I guess maybe both for carbon and methane, but I guess the idea is like in the growing season, right? Was that okay, let me look. Yeah, it seems to be more stable, I guess you could say, or constant.
Yeah.
And it's not responding really to these oxygen pulses because there's already oxygen pulses probably happening more in its growing season. That's the idea.
Yeah,
Okay.
exactly.
Yeah.
Great takeaway.
That was
Yes.
like, that felt like very important. I wanted to make sure that was straight in my mind. So,
Yeah.
Okay, cool.
Yeah, so the plant would have been already pulsing that oxygen, kind of already priming, stimulating that release prior to the incubation.
So then in the non-growing season one, you kind of were emulating that, but because it's not really happening when the plants aren't growing as much, which is interesting because I guess the plants are broken, but there's probably not as much oxygen going down. The idea is probably more oxygen, or sorry, not oxygen, just gases going up these.
Yeah, so there's 3 different main mechanisms for how these gases are transported down. They're either through photosynthesis, where it's creating these pressure gradients from humidity and temperature, or there's the Venturi effect. So as the wind blows through the stand, they're creating that pressure difference, driving the oxygen down. That one's a lot more passive and less efficient. So during the non-growing season, that would be occurring, but it's
Not as strong of a force.
yeah.
That makes sense.
Like when we're thinking about something like Phragmites, it is one of like the invasive species of Phragmites australis that we're working with is 300% more effective at oxygenating even compared to the native species of Phragmites. So we're talking about an incredibly aggressive oxygenator. So that Venturi effect's not going to really be as relevant. But yeah, great question.
No, thank you.
I had a similar thought to what Grace was just saying. So do you think that's also maybe why, as you get farther away from the highly concentrated Phragmites zones, you see more and more response in the growing season to these oxygen pulses? Because like the Phragmites would be pulsing the oxygen more where it's present, and then as you get farther
Yeah.
away, like it's not getting as many pulses.
I see what you're thinking, but it was surprising because in this growing season, we actually saw really no effect. In
Yeah, I
CO2.
mean like as the sites get, oh, I'm reading backwards, never mind.
I see your thought process though. Sorry, Dr. Baldwin, I didn't mean to skip you.
No, it's okay. So it seems like that site 3, it's more mineral soil, is that right? So maybe getting erosion from the upland nearby. And if that's the case, because you see that kind of thing along like an estuary grade, where there's
Yeah.
mineral sediment at the upper end of the estuary and then the lower end, maybe it's getting some mineral sediment from storms, but maybe it has less, and so the organic matter is lower. So if that's the case, is there also organic matter from the upland getting in there, and is that organic matter, is that pine trees? It seemed they were like hardwoods, mixed hardwood forest.
Yeah, it
Can you go
seemed
to the
mixed.
ETA really quick?
Yeah.
Like the
You
very first
see
one.
a signal of organic, upland organic matter that might be different from the wetland.
Sorry.
Yeah.
I don't know
So,
if you mentioned that.
yeah.
Yeah, so I think that organic story is definitely there, and it made sense why we were getting so much of that lignin there because it was the forested edge. It also had the most, not only the most abundant amount of lignin compared to the sites, but it also had the most diverse pool of lignin. So I do think that it could have been coming downward, or it also could have been coming up. I think it really could have been a mix, given that it's a tidal system as well.
And I want to say something too, because there's a fundamental thing that we found here that kind of throws the theory, it throws something at the theory to make it more robust when we interpret things using the thermodynamic theory. Because like what we found, well, our hypotheses were guided by this idea that smaller, more oxidized molecules are more energy rich for microbes. That's how everyone nowadays sort of uses the theory. What we found is that those things can be disconnected. The forest, we think that, okay, so the sites that we were just talking about at the wetland forest edge, they were enriched in the largest molecules that we saw in the study, but they were also they were relatively highly oxidized, which is funny because we would normally think that the large lignin molecules will be more reduced, but the ones from the forest, for some reason, they're huge, but they're more oxidized. And as soon as we hit them with oxygen, they went from the largest molecules to the smallest molecules in their study. So they're highly reactive. That's one of the really cool things, and it also makes us think about how we should be applying the thermodynamic theory for organic matter when we look at these types of soils.
Yeah,
So,
which was interesting because looking at the lignin pool of site 1, we were getting this much more reduced pool, but they were also heavier. So it was kind of interesting to see that central to the marsh and those being so far away from each other, like on the transect themselves, also yielded such different kind of, I guess, thermodynamic potentials. Yeah.
So, if I understand this correctly, all of your organic analysis was on the soluble portion.
Yeah.
And that's water soluble?
yeah.
Just DI water, whatever you say.
So-
It's actually the pore water from
Oh,
the
it's
site.
pore
itself.
water,
Yeah.
but that's, yeah, it's got a pretty low pH-ish.
6, or of the sites was about 6,
Slightly,
yeah.
slightly acid. So
Yeah,
there's no alkaline extraction here.
no.
So there's a lot that you're not extracting.
Yeah, in a way, but in our preliminary incubations, we did use DI water, and you wouldn't think of DI water as being like this corrosive kind of extractant, but in a system where we're dealing with salinity, we're dealing with so many other things dissolved, it really did take a lot out in terms of, we really didn't see much generation in gases.
And Isabelle, I have a philosophical question.
Oh, a philosophical question,
If
my
we incubate a
favorite.
soil for a month, do you think that incubation is a type of extraction?
In a way, yeah, I think it is because like we're giving it so much more time to kind of naturally dissolute into the system. And we're also seeing like, it's a 3-phase system. Yeah, we're measuring these gases and we're seeing the liquid portion, but as things are coming into solution and into the gas phase, we're then continuing to extract from that solid phase. So these are like relative abundances of these the molecular pools, but it's still important to see. That's why I think the trace lignin additions would be really cool because we can kind of see it through those phases. Yeah.
So grow plants, make living, grow plants with a pulse.
Jason, do you have some lignin that's enriched in C13 right now?
Yeah, right.
Mhm.
Exactly, yeah.
It'd be pretty cool. Yeah. Yeah.
What do you think some potential applications of these findings could be?
I think that it would be really cool to try to see if we're seeing these cram pools come up in the field, maybe not incubating the soil, but looking from the soil themselves. I do think this is really early on and it has more of a potential as a predictor of methane generation if we're going to think of things large scales. I mean, when we think about like global methane and carbon budgets, most of them don't, like the IPCC, for example, doesn't even factor in plant-mediated exchange. Some papers have found that upwards of 80 to 90% of methane generation can be coming through these plants. So I think that it has much longer down the lines applications, but yeah, I do think it would be really cool to see, is this corresponding in the field?
All right, we can give one more round.